Okay, so today we have Otat from MIT, and he will tell us about generalized symmetry and Axion standard model.
Great. Okay, so first of all, I'd like to thank you for the invitation, and not just for once, but actually for 3 times. Like because the first 2 times I was outside of US, so I couldn't make it. So this time finally I made it. So I'll be here for the entire day. So I look forward to many interesting discussions and conversations. Okay, so today I would like to tell you something about generalized symmetries and Axion standard model. And so this is part of the effort that we're trying to connect the recent formal developments about quantum field theories, especially generalized symmetries, with particle phenomenology. And so this is mostly based on this work I've done in collaborations with Ita Choi and Matthew Forston and Shuhan Shao. So Ita and Matthew grad student at Stony Brook. And as some of you may know, that Ita is moving to IAS this fall. And Matthew is the actual particle phenomenologist on our team. So we are all from like formal backgrounds, but Matthew is the person who actually teaches us like about Axion and all these things. Okay, and this work, there's also a closely related work by Matt Rees that appeared on the same day as our paper. And it overlaps with our papers on the part related to a quantization of Axion gauge coupling. And this this work is growing out of earlier work that I wrote with also Ita and Shuhan, that we're trying to understand the non-invertible symmetries in Axion Maxwell theory. And so we are basically applying that ideas to Axion standard models. Okay, so let me begin with the talk. So before talking about Axion standard model, let me first talk about standard model. Okay, so here I listed the standard model content. So usually when we talk about standard model, we say that the standard model gauge group is given by SU3 times SU2 SU1 hyper. But there's one thing that's probably less well known, is that actually there's an ambiguity in the standard model gauge group, and this ambiguity is related to a Z6 center of this gauge group. And this Z6 center is generated by Z3 center of the SO3, SU3 times the Z2 center of the SU2, and then Z6 center of the U1 hyper. So as a check, for example, you can check that, for example, the quark doublet is actually invariant under this Z6 centers. So these Z6 centers act complete trivially on all of the matters. So that means that there's actually an ambiguity in the standard model gauge group. We could have taken the standard model gauge group to be not G tilde, but some quotient of G tilde. So for example, we can take the quotient to be either Z6 or any subgroup of that. So for example, Z2, Z3, or just simply no quotients. Okay. And so throughout the talk, I'll mostly talk about the Z6 case and the Z1 case, just to make the comparison more drastic. But in the paper, we also analyzed the case where Z3, the quotient is taken to be Z3 and Z2. So so one thing you might ask is that which gauge group is the natural one that appears in standard models? So currently there's no good answers, but let me give you some examples where various gauge group can appear. Well, one example is that, for example, we can consider UV completions where it's given by the GOTS model. Okay, and one of the GOTS model we can consider is the SU5 GOTS model, or even the spin 10, or the E6 GOTS model. And if we break this gauge group down to the standard model gauge group, what we'll find is that it's actually not given by G tilde, but it's actually given by the Z6 quotient of G tilde. Okay, and a way to see that is to ask how the standard model gauge group is embedded in SU5. So for example, in the GOTS gauge group. So for example, in SU5, the embedding is that we embed SU2 and SU3 diagonally into SU5. And then we also have the U1 that embedded also diagonally as SU5. So through this embeddings, we can see that actually the Z6 center is actually completely identified between the SU2, SO3, SU3, and the U1 hybrid. So the gauge group that we get after Hicksing down is actually the Z6 quotient. Okay. So well, from the Gus model, it's very natural to get a Z6 quotient.
So that's for all of them?
Yeah, that's right. And there's a very simple reason why for all of them it's true, is because SU5 is just part of spin 10, and spin 10 can be embedded in E6. So as long as SU5 gives you the Z6 quotient, all of them give you Z6 quotient. Okay. So this is one example, and there's another example where the standard model gauge group cannot be Z6, and this is what's called a KSVZ model. So this is a model of axions, so it's axion models. And in these models, other than the usual standard model content, there's an extra fermions, and this fermions is just transformed as a color, just transformed as the 3 representations of SU3, so it's transformed into fundamental representations, but then it transforms completely trivially under SU2 and U1. So in that case, then we see that the Z6 actually acts non-trivially on that. So the quotient that we can take are only either Z2 or the trivial quotients. Okay. So there are various possibilities what gauge group we should take. Okay, so now a natural question one we ask is that given that there are at least 4 possible gauge group that we can take, which one is the correct gauge group that describes our nature? And to answer that, we first need to understand what's the difference between these different gauge groups. So this comes to the parts that relate to generalized symmetries, and this will be pretty elementary for people who actually know generalized symmetries, but nevertheless, I think it's worth reviewing. Okay, so to explain the difference between these different gauge groups, let's just consider a much simpler case. Instead of taking the gauge group to be the standard model gauge group, let's just take the gauge group to be SUN. Okay, so let's consider the case where the gauge group is SUN. And then we just consider pure gauge theory with SUN gauge group. But we know that SUN also has a ZN centers. We can ask what's the difference between the SUN gauge theory and what's called a PSUN gauge theory. So PSUN gauge theory is the one where we take the ZN quotient of the SUN. Okay. So first of all, it turns out that these two theories has completely identical local operator spectrums, and they have the same correlation functions of local operators. Okay. They have same local operator and their correlation functions. So there's no way to distinguish them just by looking at correlation functions of local operators. But they're different in their line operator spectrums. And so a way to understand that is that, first of all, in gauge theories, there are a natural line operator that we can talk about, which is the Wilson lines. Okay, and the Wilson lines are labeled by representations of the gauge group. So in the SUN theories, we can take any SUN representations. So that means that we include the trivial representations, the fundamental representations, the symmetric, anti-symmetric, so on and so forth. But in PSUN theories, the representations has to be taken to be a PSUN representations, to be a representation of the gauge group. So, but a PSUN representation means that, for example, fundamental wouldn't be considered as a PSUN representations because the ZN center acts not trivially on the fundamental. Okay, and the simplest representations that transforms as a PSUN representations is, for example, adjoint, other than the trivial representation, so on and so forth. And you see, the difference between these representations is essentially asking whether the ZN center acts on these representations or not. And we can define a ZN charge, and this ZN charge is telling us how the ZN center acts on the representations. Okay, so this is a ZN charge. So in the case of fundamental, it will act as a ZN charge equals to 1. And in the case of, for example, symmetric or anti-symmetric, because there are 2 boxes, so the representations, the ZN charge would, or the representation will have ZN charge 2. And then in the case of a joint, because it always has n boxes, so then the ZN charge is taken to be n, is n. So a way to just talk about what is the PSON representation is to demand that the Zn charge has to be 0 mod n. Okay, so that any representations with Cn charge that is 0 mod n will be considered as the PSON representations. And the reason I mentioned the Zn charge is because this is precisely related to a symmetry in this gauge series. And this is what's called a Zn one-form symmetry. Okay. So what is Zn one-form symmetry? It's just a symmetry that shifts the gauge fields by a flat connections. And since it's shifted by flat connections, this will not change the field strength. So the field strength will be invariant. So the Lagrangian will be invariant. But this flat connections has to be in the Zn centers. It has to have non-trivial holonomy. It can have non-trivial holonomy in the Zn centers. So that's why it can transform, for example, the Wilson lines. It will transform the Wilson lines by a Zn center. Okay. So in Axion theories, there's this Zn one-form symmetries. And because we have non-trivial Wilson lines that are in representations that carries non-trivial Zn charge. But in PSON theories, because the representations all transform trivially under the Zn, so that means that the Zn one-form symmetry actually doesn't exist in PSON theories. And this is precisely how we relate the Axion theory with PSON theories. That is, start with the Axion theory, where we actually have the Zn one-form symmetries. We can gauge the one-form symmetries, okay? And when we gauge the Zn one-form symmetry, we'll get the PSON theories. And gauging the Zn one-form symmetry basically means that we project out things that transforms non-trivially under the Zn one-form symmetries, right? And if we look at the Wilson lines, that can, for example, in the fundamental representations, we will transform non-trivially under the Zn one-form symmetry. So that's why it will be projected out after we gauge the one-form symmetry. And we only left with representations that are PSON representations, okay? So, and in fact, this is also a reason why local operator doesn't, it's not a fact that local operator correlation functions is always the same, because the two theories are related by gauging a Zn one-form symmetry. But Zn one-form symmetry only acts on line operators rather than local operators. Okay, so other than Wilson lines, the theory also has what's called the Topf line. So a way to characterize, so what is a Topf line? A Topf line is just the world line of monopole, of a probe monopole. It's just like a Wilson line is a probe line of it's a world line of a probe quark. So to describe a Topf line, what we do is that we'll take a Topf line in space-time, then we will carve out, let's say we'll take intersections at a fixed time slice. Mm-hmm. Then we'll carve out a sphere, a ball around it, and then we just ask what is the gauge bundles on that spheres. Okay, so this is just like how usually we construct monopole configurations in U1 gauge theories. So let me take the following subgroup of SUN. So I'll take a U1 subgroup in SUN that is parameterized by these generators. And let me also consider gauge transformations. Let me call this generator T. Then let me just work with this gauge transformations. Transformations that are also exponentiations of this Lie algebra elements. Okay, so now we can consider the same things that we will do when we construct monopoles. So let's take the sphere and then we divide it into north pole and south pole. Okay, so then we have the gauge fields at the north pole, and then we have the gauge fields at the south pole. But then when we glue them, we allow to have to allow them to be in non-trivial configurations. Okay, and this non-trivial configurations is that we allow to glue them by some gauge transformations, where I use the G that is the exponentiations of this the algebra elements. Okay, and so if I so here this I can take the parameters that parameterize the group elements to be depending on the equators, the angles on the equators, which are parameterized by phi. So then if I look at the gluing of the gauge fields at north pole and the gauge field at south pole, then that differ by just the gauge transformations. that are parameterized by lambda phi. Okay, so in Axion theories, let me erase this. So in Axion theory, my lambda parameters is U1 parameters. So I can take my lambda to be a function that linear in phi. Okay, and the coefficient is has to be fixed to be an integer, so that when I go around this equators and come back to identities, right? That when I go around equators, that g phi plus 2 pi is just the same as g phi. So the gauge parameter is exactly go back to itself. And so this will define for me multiple configurations. But in the case of PSON theories, notice that I'm gauging the Zn group. So that means that when I let the gauge parameters to go back, it doesn't need to go back exactly to itself. It can go back to itself off by a Zn phase, because the Zn is actually trivial elements in PSON. So then I can take my lambda to be phi k divided by n. Okay, and then my gauge transformations will come back to itself up to the phase. So what they're saying is that if I look at the gauge bundles on a sphere, then there are actually more at PSON gauge bundles than Axion gauge bundles, because my Zn is actually trivial. So then I allow my gauge parameter to come back to itself off by a Zn phase rather than exactly come back to itself. Okay, and if I translate it back to language of TOF lines, that means that there are actually more TOF lines than in PSON theories than in Axion theories. So this is to be contrasted with the Wilson lines. In the case of Wilson lines, there are more Wilson lines in Axion theories compared to the PSON theories. Okay, good. And now I talk about the topology of the gauge bundles of spheres. Then we can talk about topology of gauge bundles on the space-time. Okay. So this is the second. This is the third difference between the Axion versus PSON gauge group. So they're actually also different in their instanton number. So this will be very crucial for our discussion later. Okay. So instanton number is just defined to be integral of trace Fyj. So let me, for simplicity, take my spacetime to be just S2 times S2. Okay. Then I'm allowed to consider non-trivial gauge bundles on both S2 and times S2. And then we just compute what is the instanton number for that. So we know that in Axion, which is the common result, is that the instanton number is always an integer. But in PSON, which will be crucial for our later discussion, is that the instanton number is actually can be taken to be 1 over n times integers. So there can be fractional instantons in PSON. Okay, and the way to understand this fractional instanton is again very simple. That we can do the same explicit construction as before. So let's just consider. Let me do the same. Let me just consider the same U1 subgroup in Axion as follows. Then the instanton number, in this case, will just be 1 over 8 pi squared, n minus 1 times n, and little f dash f, and the integral of that. Little f will be just the field strength of A. Okay, and we know that in PSON theories that the integral of f on a sphere is essentially just the difference, because f is just the integral of dA, right? So we can divide it into north patch and south patch. Then using Stokes theorems, it's just telling us that it's a difference between an and the gauge flows at the north patch minus the gauge flows at the south patch, and then we just need to ask integrate the difference on the equators if I use the Stokes theorems. Okay, and then now using the gluing conditions, then this is telling us that this is essentially just the integral of the d lambda phi on the equators. And this is essentially asking how many times this lambda parameters is winding around the sphere. So in the case of Axion, because this lambda, as I said before, has to wind around always by 2 pi times integers. But in the case of PSUN, this lambda can wind around by 2 pi over n times integers. So that means that the integral of f in PSUN theories can actually be 2 pi m divided by big N. Okay, m is taken to be an integer. Okay, so if I plug in this back to here, that I'm allowed on one of the sphere to have flux n, and the other sphere to have flux n total, then the instanton number, if I evaluate it, it will just give me n -1 divided by n times m total. Okay, and this thing is nothing but -1 divided by n times n total mod 1. Okay, so here we see that we actually explicitly construct fractional instanton configurations using the monopole configurations that we constructed before. And this fractional instanton configurations carries instanton number that is 1 over n. Okay. Okay, so this is basically done with the review of the difference between SUN and PSUN theories. So let me just summarize. So from what we learned from SUN, the comparison of SUN and PSUN theories, that they are completely identical if we look at their local operator spectrums, but they are different in sort of the topological aspects of the theories. So for example, they have different Toph lines and different Wilson lines, and also they have different instanton numbers. So, but then this poses problems to the questions that I asked before. So because we know that there's this ambiguity in the standard model gauge rule, which is just differed by the quotient of the centers, right? But then I told you that all these theories are locally indistinguishable. So that means that if we just look at scalar amplitudes of local operators, made of local operators or particles, then we wouldn't be able to distinguish them. Okay, so it seems that there's nothing we can say about this. But then one of the punchlines that I want to give is that actually the axion, once we have axions, then axion can actually tell the difference. Okay, so it can actually tells you, it actually, for axion, it actually matters which quotient that you take. Okay. Okay, so that's what I'm going to explain next. So now I'm going to turn to axions. So first of all, let me first just give a short summary or introductions to what is axions. So axions, in short, is a periodic scalar. So it's a periodic scalar, and to be more precise, it's actually a pseudo-scalar, meaning that it actually transforms under the CP transformation. So it's odd under CP transformations, and then and it's a pseudo-scalar that coupled to instanton density. So I'll consider the simplest example of axions coupled to standard model. So which is just having first of all the usual axion kinetic terms. I'll use theta to denote my axion field. And I'll always work with the normalizations where axions are normalized to be 2 pi periodic. Okay. And then I'll couple these axions. I just have single axions. And I'll couple these axions to all of the standard model gauge group. So means that we'll have something and F1 is the gauge field for the U1 hyper. F2 is the gauge field for the SU2, and then we also have the gauge field for the SU3. This is the standard model. This is the model that I'm going to consider from now on.
You just do it, make them all the same to be simple, or anything deeper than that?
No, nothing deep. It's just I'm just considered simplest model. Yeah, I'm just considered simplest model. That's right.
They're not the same, right? They're Ks.
Oh, sorry. Are you asking K? Are you asking why this axion fields are?
Well, just put it in, well, even just putting them in.
Oh,
I suppose you could say one of the case to zero is a special case.
that's right. Yeah, that's right. And just consider this. Yeah, yeah, that's right. Yeah. Oh, and also this K in general can be different. Okay. So also before I proceed, let me just make a few comments why we care about axions, just from the particle phenomenological sides. So one reason is that axion originally was first proposed as a solution to strong CP problems. So what is strong CP problems? It is a curious observations result from experiments that if we look at the theta angles for QCD, okay, this is something that the experiments can actually measure. And that theta angles turn out to be extremely tiny, and so far we don't have actual value of that. We only have an upper bound for that, and that upper bound is 10 to the minus 10. Okay, so it's extremely tiny numbers, and then this poses sort of a naturalness questions that why is the QCD axion theta angle so tiny? Okay, and so of course one natural way to explain that is that if there's a CP symmetries, that then this will solve the problem, right? Because if there's a CP symmetries, it will change the theta angles to minus theta angles. And if there's an actual CP symmetry, this will just ping the theta angles to be zero. But of course, we know that our universe actually doesn't have CP symmetry because the electroweak sector of standard model actually breaks CP. So that's why it's called a strong CP problem, that we cannot use the CP symmetry to explain this tiny axion, tiny theta angles. So then axion was proposed as a potential solution to that. And the idea is very simple, is that we should promote all of the theta angles to be actually a dynamical field, okay? And once we promote them to a dynamical field, then the instantons in the SU3 instanton will actually generate the potential for this axions. And then the axions will fall into the minimum of that SU3 potentials, which is at the theta equals to zero. And so this gives a dynamical reason why the theta angle is very small. So we are essentially seeing the vacuum excitation values of the axion field. And then at the minimum, it's just have axion field, had a vacuum excitation value that is close to zero. So this is the dynamical explanations of the strong CP problems. So there are other reasons to consider them is that they are also a good candidate for dark matter. And in fact, there are tons of experiments that are actually searching for axions right now. So I'm going to show a plot later that just demonstrate how much experience that is actually have done to try to understand axions. And also, they are, from string theories, they're also very natural to arise because in string theory, we expect that there shouldn't be any free parameters. And then when we see the theta angles for QCD, it should really be thought of as a graph of an axion field, of a dynamical field. Okay. Okay, so that is a sort of the motivation why we want to consider axion coupled to standard models as for particle phenomenology. Okay, so now let's talk about how the different choice of standard model gauge group can affect the physics of axions. Okay. So first of all, one thing that's important is that this coefficient, this axion gauge coupling coefficients, Ki, should be quantized. Okay. So let's first do the simplest example. Let's take the standard model gauge group to be just a simply connected one, where we don't do any quotients. Okay. So in that case,
for that, can I just ask one quick answer before you go? If you write just the standard model coupled to the axion like this, what is the sort of symmetry principle that allows you to not write any other term at that scale?
No, any other terms. What kind of term do you have in mind?
Well, right, roughly speaking, you are not, for example, you're not coupling the axion to any standard model fields because you're imposing something. Maybe you have in mind imposing something like a shift symmetry. On the other hand, these couplings break the shift symmetry. So you could have added to this Lagrangian at this scale something like cos theta with some coefficient, but you didn't do that.
That's right.
I was wondering what the rationale is.
So axion potential, that's a good question about axion potentials. That in principle, there's no symmetry reason. In this case, there's no symmetry reason to add the axion potentials. But if I work below the electroweak scale, there's actually an emergent symmetries there. So, but then that is not a symmetries in the standard models.
So it's an assumption that in some kind of minimal model.
That's right, it's an assumption. And let me say it's also assumptions that were made in a lot of literature in Axion. So yeah, that's right. But yeah, and the things that I'm going to say relate to the connection to phenomenology actually depends on the fact that I didn't put in the axion potential at the scales. Yeah. Okay. Okay, so let's just work in the case where the gauge group is simply connected. Okay, so first of all, we know that axion is 2-pi periodic. So our actions, or to be more precise, our partition function should better being very under shifting axion field by theta. Sorry, by 2-pi. Okay, so let's just look at the integral. The things that we want to actually look at is the Boltzmann weight, which is exponential I actions. So these things, if we shift theta by 2-pi, will be shifted by exponential 2-pi I P1 N1 plus K2 N2 plus K3 N3. And so N1, N2, N3 is just the integral of F1 trace F wedge F, sorry, F2 wedge F2 and trace F3 wedge F3. So those are the instanton numbers. And in the case of when a gauge group are simply connected, all these instanton numbers are integers. So then for the exponential IS to be invariant, all we need is just all of the quantizations, all of this axion gauge couplings to be quantized to be integers. Then the action is well defined under shifting theta by 2-pi. So in some sense, the quantization of the axion gauge coupling is fixed by the gauge symmetries of the axion field, or the 2-pi periodicity of the axion field. Okay, but now things will be different if I take the standard model gauge group to be the Z6 quotient of the simply connected one. Okay, so first of all, to understand how the quantization is modified, we need to understand how does the instanton number look like in the quotient theories. So again, I will do the same things as before. I will just pick some particular subgroup. So I'll pick a subgroup where I take A1 to be just the usual one, and then A2, which is S2 to gauge groups, to be a U1 subgroup, and then A3 to be a U1 subgroup that is like this. Okay. Then so maybe erase this. And remember the Z6 quotient that we have is the one that acts on the U1 as exponential I, sorry, at the 6th root of unity, and SU2 as a minus sign, and then on the SU3 as a Z3 center. Okay. So let's first ask what happens on S2. Okay. What are the non-trivial bundles that can exist on S2? So on S2, what can happen is that the integral of F1, which is the integral of dA1, can be actually fractional, and the fraction is coming from this Z6 quotient. Okay, and and the fraction is given by the minimal fraction it can be is 1/6 times some integers. Okay. So let me work with this quotient. Oh, sorry. So let me just parameterize the flux by this number n. But then because I'm doing a quotient that are correlated, so then that means that A2 and A3 can also have fractional flux, and the fractional flux in A2 and A3 are also controlled by this number n. Okay, and so integral of F2, which is just the integral of dA2 on this sphere, is given by m/2 mod 1. The integral of F3 is given by n over 3. So all these numbers can just be fixed by doing the same construction that I did before, asking how the gauge parameter winds around as you go around the equators. Okay. So this is what happens on S2. But now let's ask what happens on S2 times S2. So on S2 times S2, we can compute an instanton number. So instanton number in this case, which is given by 1 over 8 pi squared, integral of f with f, so f1 with f1. And this is just given by a square of this, so it's m squared divided by 36 mod 1. So what about n2? So n2, well, again given by square of this, so it's n squared over 4. But then remember there are two u1, so actually we need to multiply by a factor of 2. So it's given by m2, m squared over 2. And then n3 is given by m squared divided by 9. But then because we need to take this sum of the square of these things, so this in total will give me a factor of 6. So the instanton number can be taken to be 2 over 3 times m squared. Okay, so these are the fractional fluxes, fractional instantons that can exist in this gauge group, and they are correlated in this particular way. Okay, so then now if we plug in these things back to here and require these things to be integers, then what we learn is that we get the following conditions. The condition is given by k1 divided by 36 plus k2 divided by 2 plus 2 over 3, k3 equals to 0 mod 1. Okay, and so if you stare at it a little bit more, then you can see that it actually demands k1 to be integer multiple of 6, k2 and k3 to be integers, and then if we multiply everything by 36, then we just get these conditions. Okay, so this are the how the quantization conditions are modified if my standard model gauge group is not simply connected by a Z6 quotient of them. Okay, so far I'm just telling you how things are modified by the quotients. But now let's try to connect it with actual experiments. Okay, so first of all, let's ask what can experiment do? So what an experiment can do is that it can measure at least two things. It can actually measure tons of things, but then there are two things that it can do. So it can measure the axion mass. That's one thing, and it can also measure the axion coupling to the standard model to the photons. Okay.
So I can ask you something. So
Yes.
why is the sum constrained to be integer and not just each of the three terms separately?
Each of the three.
Yeah, k1 over 36, k2 over 2, and we're just requiring the sum that is.
Oh yeah, it's because remember that when I say they have fractional fluxes,
It's the same m for a.
that's right. They're controlled by the same n, and that is because the quotient I had is a correlated.
Yeah, sure.
Yeah, that's right. Okay. So what are the things that can be measured experimentally? One is the axion coupling to photon. So it's a so it's axion coupling to photon, and the other is axion mass. To make connections with the experiments, let me first, instead of working with the standard model, let me just go down a little bit. Let me allow the theory to go through electroweak symmetry breaking first, okay? And the reason why I can work with that is because if you think about the dynamics, what happens is that first you go through the electroweak scale, which is roughly 100 GeV, and then at roughly 100 MeV, then the QCD scale is kicking, and then you will actually generate instanton effect, and then the instanton effect will actually generate an axion of mass. So that's why I'm allowed to work below the electroweak scale, okay? So if I work below electroweak scale, in literatures, this is how people parameterize the couplings. So there's a strange factor of 2 that this unfortunate strange factor 2. So there's this is the coefficients of axion coupled to the QCD, just as before, where so this n is given by k3 over 2. And then we also have the axion coupling to the electromagnetic field. Okay. And then there's a coefficient E. And this coefficient E is related to the standard model couplings by 1 over k, 1/2 k2 plus 1 over 16 k1. Okay, so this can be worked out by just looking at the standard model, how standard model break the how the electroweak gauge group is broken to electromagnetic gauge group. Okay. And so it turns out that the axion photon couplings and the axion mass are precisely fixed by this N and E. And this is actually related to things that Thomas is asking. So, first of all, let me give you the formula for axion mass. Okay, so axion mass is given by 5.70 mu eV, 10 to the 12 GeV divided by the axion decay rate and then divided by n. Okay, so first of all, let me give you a rationale of how we compute the axion mass. So we are assuming that there are no axion potentials at the standard model scale. Okay, to be fair, we don't even need to. We actually, to be fair, we're actually assuming that at the electroweak scales there's no axion potential. Okay, and so all of the axion mass is just generated because of the instanton effect, because of the QCD instanton effect, that generates a non-trivial potential for the axions, and that gives you the axion mass. So that's why the axion mass are just fixed by the coefficient n. So it only depends on this coefficient n. Okay. And also related to the things that Thomas asked is that if I work with just the electroweak Lagrangians, there's actually an emergent symmetries in this electroweak Lagrangians. That there's an emergent Zn symmetries. So if I shift theta 2 pi over n, then this is actually a symmetry of the theory. But this is a non-invertible symmetries. But I don't want to get into that.
What scale?
Electroweak scale.
Not some of this.
Just this theory. Just if I
After Higgs.
After Higgs, yeah, that's right. Below the electroweak scale. Yeah. So this theory has an emergent non-invertible symmetry, but it's a Zn, sort of a Zn parameterized non-invertible symmetry. But it's very easy to understand, right? Because if you shift theta by 2 pi over n, so this thing is invariant. So only this term will be changed.
So this is broken by SU2 instanton.
That's right. It's broken by SU2 instantons. That's right. Okay. And this symmetry will be important for later things that I'm going to talk about. Okay, so I told you about axion mass. Axion mass is just complete controlled by this factor of n. But what about the axion photon coupling? So axion photon coupling is just given by alpha over 2 pi. So this alpha is just the phi structure constants 1 over 137, and then 1 over n minus 1.924. Okay. So let me explain this formula. So this part, so of course, axion photon coupling should definitely not depend on E now, right? I think you would say it should only depend on E. So that's correct if you look at this part, okay? If you just look at this part, then the axion photon coupling only depends on E. But this is the bare coupling. But then if you if you go under the QCD scales, then what happens is that we will go through chiral symmetry breakings, and then we will generate the neutral. We'll have pions, but then neutral pions will actually couple to photons also, and then you need to worry about the mixing between the axion field and the neutral pion fields, and that generates this piece. Okay, so this is the piece that relates to the mixing of axion field and the pion field. So together they give you the full answers. That is the axion photon coupling. So these are the things that can be measured experimentally. And one nice thing is that, you see, if I take the ratio of that, then the F over N cancel out. So that means that if I take the ratio of these two things, I can actually measure E over N. Okay, so this is the things that can actually be measured. And but of course, here I'm making the assumption that I'm working with just this Lagrangians, that I'm not putting any Axion potentials. Okay, good. So now let's ask what can we do with this quantization conditions? How can we use these quantization conditions for experiments? Okay. So first of all, this quantization condition, if we translate it to this coefficient E and N, then what it gives is that if give the following conditions, that 3E plus 4N has to be 0 more 3, and I can take my N to be half integers, and E to be 1/3 times integers. Okay, so this is the quantization conditions. If I translate what we learned about Axion standard models to this coupling E and N. Okay. Okay, so because of these quantization conditions, and we know that E and N has to be integers, then we know that this E over N coefficients supposed to take some rational numbers, right? It's just integers over integers, so it has to be some rational numbers. But then telling you that this rational number actually doesn't buy much, that you didn't get much mileage because we can always approximate real numbers by rational numbers. But then there's one input that I will need. It's related to what's called domain wall problems. So what is domain wall problems? So domain wall problems is the following. So if we assume that the Axion potentials are generated by just the QCD, just by the QCD instantons, then the potential that we get will have multiple vacuum, and the number of vacuum is fixed by n. Okay. Oh, so it's fixed by n. So the number of vacuum, which is also related to number of domain walls, is given by 2 times n, or it's given by k3. Okay. And this is related to the non-invertible symmetries that I talked about. That because of this non-invertible symmetries, that the potential that we generate would have multiple vacuum. So this is a value. So this is, for example, the Axion potential. Okay. So now we can ask, well, what happens if this K3 is greater than 1? Okay. If K3 is greater than 1, then what happens is that I can consider the following configurations where theta winds around by 2 pi. Okay. So the Axion field just winds around by 2 pi. So if Axion fields wind around by 2 pi, then it will go through multiple vacuums. Okay. So that means that if I look at the energy profiles, then I'll actually get multiple domain walls, right? Because I'm climbing the potentials. So as I go from one vacuum to the other vacuum, I'm climbing the potentials. And how many potentials that I climb as I come back is related to the number of vacuums that I have. So if the number of domain walls is greater than 1, that means that I have multiple domain walls that comes in and they meet at the domain wall junctions. Okay. But this is actually a big problem. So if this domain wall are formed after inflations, because if this domain walls are formed after inflations, they're actually stable things, right? That I cannot let these things decay. This is something very stable. That for example, imagine that I have the other things here and things like that. So these junctions are something very stable. But then we don't see them in our universe. So that's why if this domain walls are formed after inflations, then these are actually in contradictions with observations. So, but if they're formed before inflation, then there's actually no problems.
Can you explain that a little bit more? Because since this Zn is broken by SU2 instantons or whatever, so you would expect the breaking to be
tiny. I mean, expect the breaking to be.
No, you would expect it to be not that tiny. If you're early enough in the universe that your temperature is high and you kind of people use SU2 transition instantons for all sorts of things like baryon, lepton asymmetry, and so on. So why can't imagine that you're after inflation, but the universe cools, but it's still very hot. Right, you're still above the electroweak scale, and SU2 instantons are all over the place. Why can't they just break the symmetry?
Oh, so when this domain wall are formed, I'm already below the electroweak scale.
But you said after inflation.
Yeah, after inflation, yeah, therefore, but
there's a lot of time between inflation and electroweak symmetry breaking, right?
Oh, sorry.
When things are very hot and
Let me but no, because the height of this domain wall is given by QCD scales. So to actually have this domain walls, you actually go below QCD scales to have this domain wall.
no, but the height is what it is, but
Yes.
these three vacua are not exactly degenerate, right? The degeneracy is split by the small SU2 effect.
Yeah, it's split by very, very tiny.
So it's not big enough to be interesting.
That's right. Yeah, that's right.
That's the claim.
Yeah, that's a claim. That's a claim. Yeah, that's a claim. But things would be very different if this number of domain walls is just one, right? If the number of domain walls is one, then you basically just have a single vacuum. So your potential would not be like this. Your potential will be like this. Then we have the domain walls. Then you just have a domain wall that end at the axion strings. So things will just shrink gradually. Yeah, but these things will be very stable. So there's a difference between the case when domain wall equals to 1 and domain wall equals to or greater than 1. Okay. So this is the assumption that I want to put in, that I want to take the number of domain walls to be 1. Okay. So once the number of domain wall is 1, then because of the quantization conditions, then we see that these things can actually take discrete values. So it's some coarse discrete values. And then now we can actually use it to bound the axion photon couplings. So we just need to find the number within these discrete values that satisfy these conditions that is closest to 1.92. Then we can bound the axion photon couplings. Okay. So let me just give the punchline now. So the punchline is that if we want to avoid domain wall problem. So first of all, let me say that the domain wall problem can be avoided already if the domain wall formed before inflations. But suppose we want to avoid that, then we want to take a number of domain wall, which is K3, 1. Okay. So in that case, then E over N can only take some discrete values. And it turns out that we can use it to bound the axion photon couplings, or the ratio of axion photon couplings and the photon mass. And the axion mass. And this thing has to be greater than the time to normal. Oh, sorry, I think I didn't have the number here. But okay, but you can ask what is the closest number of E over N that is closest to this? And it turns out the closest number that satisfies this condition is given by A over 3. Okay, and this A over 3 is a sort of a magical numbers. If you study axions in the past, is that happens to be the numbers that show up in 2 places. One is the famous DFSZ models. So this is one of the benchmarking models in Axion. When people study axions, they give you exactly 8 over 3. And there's another model is that if we consider a single axion coupled to guts, this also gives you 8 over 3. So this happens to be some coincidence that the minimal axion photon couplings that you get is coincides with the 2 benchmarking examples. Okay, and I think I almost run out of time. So let me just show you one figure.
It's not hard cutoff because the pizza won't get here for another 15 minutes.
Okay, sure. Then I can talk about some other things also. But I want to show the how this bound is compared to the experiments. I'm almost done with so this is basically a punchline that this quantization conditions together with the domain wall problems can use to give you a lower bound on this axion photon couplings. And I want to just show you a figure how to compare that. And after that, I can talk a little bit about the fate of the Z6 symmetry if people are interested in that. Okay. Okay, so this is the plot that you can find online. So this is the axion mass, and this is the photon coupling, the axion photon couplings. So these are all the experiments that exclude the regions. Okay, so these are all the exclusions. And so the claim is that if our standard model, so let me say things again. So if our standard model gauge group is a Z6 quotient, and if you want to avoid domain wall problems, then the claim is that we should be above this line. We should be to the left of this line to avoid domain wall problems. If we're to the right of this line, then there are actually domain wall problems. So these are the result we get. And this line is also where the two benchmarking examples are lying at, the DFSE models and the Axion couple two guns. Okay, so
if something generates axion potential, like can this line shift arbitrarily, or like do you lose complete control?
yeah, so if you have the axion potential already at less than the electron weak scale, then what I said would not be correct. Yeah. So you will, I think you will. Let me think. I think you will move this line will move this way because you will get extra contributions from the potentials. Yeah, that's right.
That's why you can also get less. I mean, what fixes the sign of the potential?
That's fair. That's also fair. That's right. That's right. Yeah. So I think that's fair. Yeah. That's right. So I shouldn't make any. Yeah. So yeah, but of course I put in a strong assumption that I'm working with this Axion coupled to standard models, and then I'm not putting any potentials.
Other than that, it's kind of a minimal assumption. Is there some reason that people believe that this should be true?
No, actually. So, but this is where the actual you can start making expectations. So for example, remember the two formulas that I wrote about axion photon couplings and the axion mass, and those are derived assuming that we just have the axion coupled to. They actually, I think, just assume at the electron weak scale that the axion is coupled to the SU3 sectors and the U1 through that particular coupling. Yeah, that's right. And without axion potential, it's just so that you can have something to benchmark.
But in these, for example, in these gut models that you mentioned, you said that one of the minimal 8/3 models is a gut. If you set the axion mass to 0 at the gut scale, wouldn't it be generated by gut instantons by the time you get to the electroweak scale?
That's true. Yeah, that's fair. That's fair. Let me think.
Like instantons in the broken part of the group.
That's right. Yeah, yeah, that's right. So if you reduce to the electroweak scale, you already get some axion potential.
It's very tiny, but
yeah, it will be very tiny. I think that's the assumption that people are putting in that whatever things that you get are very tiny at the electroweak scale. Just right after electroweak.
Is that related to like the quality problem for QCD axions? Like, there's like some UV effects that actually don't give you small contributions to the axion.
That's right.
That's specific to QCD axions, but maybe it sounds related to this.
I think it's related to quality problems. But first of all, I have no saying about quality problems, so let me don't get into that. Yeah, but yeah, it's really related to that. So this is the things that we can make. So I don't want to overclaim anything, but this is just the model things that we can make. Okay. So let me just okay. So now I sort of done with the multiple parts. I can now another sort of questions one can ask is I mentioned that there's this Z6 symmetries, right? That we start with before just in the standard model before we couple to axions. We can ask what is the fate of that Z6 symmetry? Okay. Like and that what can we say using that Z6 symmetries? Okay.
So that's sort of the second part of the talk. So should I continue or? Okay, good. I'll just I will say something very briefly about the fate of that Z6. Okay. So okay. So let me just write the action again. Okay, there's a there's a case that comes after that. Okay, so before we turn on a couple of the standard model to axions, we know that there's a Z6 symmetry, right? Z6 one-form symmetry. But then after a couple to axions, the Z6 one-form symmetry actually is broken down to. So first of all, you would say it should be broken. Why it should be broken? The way to think about that is that in this theories that we can consider toe lines. Okay, so in this theories, because so first of all, other than the Z6 one-form symmetry, if we turn on the axion potentials, axion, if we introduce the axion fields, then there are two additional symmetries that you can talk about. One is the U1 magnetic one-form symmetry. This is just generated the current, just it's just a U1 hyper. It's just a current for the it's just a field strength of the U1 hyper. Okay, so and this thing itself is automatically a conserved current. So this defines for you magnetic one-form symmetries. The things just charged under this one-form symmetries. Actually, let me just put a factor of 1 here. So this is the gauge fields for the U1 hyper. Okay, and the things that charge under this magnetic one-form symmetries is the toe line. For U1 hyper, U1 hyper.
Right, I will consider the simply connected.
And consider. No. So far, if I talk about this, the two symmetry wouldn't depend on whether the gauge will be simply connected or not. Yeah, but the Z6 will depends. Yeah, that's right. Yeah, I'll come to that soon. I'll come to that soon.
U1 is never simply connected.
Sorry?
The U1 is never simply connected.
The U1.
One was
Yeah, that's right.
stickler.
Yeah, but this part wouldn't be affected by the gauge group, the choice of gauge group. So other than that, there's also U1 winding symmetry. Okay, so this is related to the axion string, and the current is a three-form current. So that is just 0.5. Okay. And again, this is a closed. Okay. And then the things charged under this is the axion strings. So what this symmetry is doing is just measuring how axion winds around the axion strings. Okay. So these are the two symmetries that doesn't depend on the standard model gauge group. Okay, but now let's ask what happens with Z6 or one-form symmetry. So just as one was asked, so if the standard model gauge group is just taken to be the Z6 quotient, okay, then there's actually nothing to talk about. That the Z6 one-form symmetry is gauged. Okay, so there's nothing to talk about. So now let me just focus on the case where the gauge group is simply connected. Okay, so there, because the Z6 is not gauged, then I can still ask what happens to this Z6 after I couple to a standard model. Okay, so so it turns out that first of all, this Z6 is broken down to the GCD 6K1. If we just look at the invertible one, okay? And the way to understand that is the following: that imagine that you have some probe monopoles for the U1 hyper, okay? And then also imagine that you have axion strings. So axion string is characterized by the fact that the axion fields will wind around by 2 pi, okay? Now you can imagine doing the following: that you pair create two hypercharged monopoles, okay? So one with a positive charge, the other with a negative charge. And then we bring them around, okay? So if we bring them around, then because of the Witten effect, that the Witten effect is saying that the charge, the electric charge of the monopoles would depend on what was given by theta over 2 pi mod 1. Okay. But we know that theta is exactly 1 around by 2 pi. So that means that if I bring the monopole and anti-monopole around and let them annihilate on the other side, and I'm actually left behind electric particles. So I have a particle whose electric charge is 1. Okay. So actually, to be more precise, it's actually K1. It's fixed by this coefficient K1. Okay. So that means that I can actually create Wilson lines out of Otof lines that I can just let the Otof line wrap around Axion strings. Then I will have a Wilson line that's just emitted from the Otof lines. Okay. So because I can create a Wilson line out of nothing, so then that means that my symmetry would be broken. And the symmetry that would be broken is the one that is broken to this particular subgroup. Okay, because the things the Wilson line that comes out, it has a charge K1. Okay.
That sounds sort of like a dynamical argument. Like you actually have dynamical monopoles that could.
Yeah, the way I phrase it sounds like a dynamical argument, but what I'm talking about is probe particles. Yeah, so you can actually draw things in a language of just defect operators that you have a Wilson. You have, so basically instead of drawing a monopole here, you can actually draw actual Otof lines, okay, and then that wrap around, and then there will be a Wilson line that comes out. So this is, and this has to be the case actually, that you can check that if there's no Wilson line come out, then correlation function is vanishes.
Okay. Can I say it another way by saying that if you take this Axion string, there'll be a Chern-Simons term that's somehow like emanating from the string.
Chern-Simons
Right, if you just take that formula and indicate there's a Chern-Simons term in the bulk that kind of acts like anomaly inflow.
Right.
in the string.
It's, yeah, maybe the.
So this is the usual breaking of the one form symmetry in the Chern-Simons term at level K.
That's roughly correct. Yeah, but I think maybe the correct thing is to talk about Otof lines, maybe. That there are anomaly inflow to the Otof lines. Because I'm saying that the Wilson lines.
Symmetry is the electric one form symmetry.
That's right. Yeah.
So
I'm saying that the things can emitted from Otof lines, right? A Wilson line is emitted from the Otof lines, and then if you
that's also true in Chern-Simons theory.
Sorry.
That's also true in Chern-Simons theory, right?
That's also true. Yeah, that's also true. Yeah. Okay. So maybe the things that you had in mind is the following. That let me draw another things. You can imagine that you have a domain wall. Okay. So and then the axion field 2 is changed from 0 to 2 pi. Yeah. Then here there will be a sort of U1 level K1 Chern-Simons theories.
Right, but you can also wind it into a string, and then you'll of the string world sheet, and you can take an open 3 surface at the end of the Axion string. So you can do the same thing in both cases. Right.
Sure. Yeah. Sure. Sure. So
be attached to this surface.
Yeah.
Because of this term.
Yeah.
yeah. So that's fine. That's actually fine because actually I didn't say one thing. I didn't say is that actually there's also a Wilson line that has to come out from the Axion strings also.
Right. There's like charges on the.
That's right.
On the Axion string.
Yeah. So yeah, you can understand this also from the anomaly inflow perspective. That's fine. That's right. Okay. So the symmetry is broken from Z6 to ZGCD. Okay. But that's actually not the entire story. The entire story is that the things that we thought are complete, the things that we thought are broken, namely the things that in the quotients actually becomes non-invariable. Okay, so then the symmetry structure, roughly speaking, is something like a non-invariable symmetry non-invariable symmetry is extended by this unbroken part, and then they form the full Z6 quantum symmetries. Okay, and but I don't want to get into too much details of the non-invariable symmetries. But then there's one thing I want to mention is that suppose you have this non-invariable one-point symmetries, okay? And the non-invariable one-point symmetries is defined on some surfaces, okay? And then so you can imagine that I fuse two such non-invariable one-point symmetries, then you can ask what is the things that we get. So the things that we get is that we'll get a sum of symmetry, the symmetry operators for the magnetic quantum symmetry. And then we also get some of the symmetry operators for the winding symmetry. Okay. So this is very important for the next thing I'm going to say. That is, you see, for this non-invariable symmetries to exist, then we actually require the magnetic symmetry and the winding symmetry to exist. Okay. But now imagine that in this theories that there are some Z6 some massive particle that kick in that breaks the Z6 quantum symmetries. Okay. Then if I break that Z6 quantum symmetries, then I will necessarily have to break these two symmetries, right? And I'll necessarily break the non-invariable symmetries. And then because we know that sorry, actually, I think I said. Yeah, we'll break the non-invariable symmetries. But on the other hand, we can also ask how we break the magnetic symmetry and the winding symmetries. What we need is that we have a dynamical monopoles. The dynamical monopoles will break the magnetic symmetries, and the dynamical Axion strings will break the winding symmetries. So the important thing is that once magnetic symmetry, all the winding symmetry is broken, then the non-invariable symmetry has to be broken. Okay. So then we actually get the following inequalities. If I do the following interpretation that so I'll get the following inequality that the mass of the magnetic monopole or the Axion string tension should upper bound the mass of a Z6 charged particle. So if there's this non-invariable symmetry. So if there's a non-invariable symmetry. And for there to be non-invariable symmetries, we basically need the K1 to be not divisible by 6. So this is one inequality that we can derive from this symmetry analysis, that the monopole and Axion strings actually upper bounds the Z6 charged particles. Okay.
And again, because like you need like if you break only one of them, then break.
I mean, if I break the magnetic symmetries, yeah, if I break magnetic symmetries, this will be broken already. So that's why exactly the minimum. The minimum of either this or this with the upper bounds. Yeah. So that's one thing that we can derive from this symmetries. And there's another things we can derive. Is that suppose now we take K1 to be divisible by 6. Okay. So if K1 is divisible by 6, then I'm actually not breaking any of the symmetries. All my symmetries remains invariable. So I cannot make any statements based on the non-invariable symmetries. But there's actually a higher group symmetries that's hidden in the story. Okay, so there's a higher group symmetries. So the higher group symmetry is a symmetry that makes the Z6 quantum symmetry with the U1 winding symmetries. Okay, so what the symmetry is telling you is that if I turn on the backgrounds for the Z6 quantum symmetries, I have to turn on the background for the winding symmetries. So that means that if there's a higher group symmetries, then if I break the U1 winding symmetries, then the Z6 symmetry has to be broken. So it's similar to this philosophy. Here, things comes from the fusions. Here, things comes from something else. Some come from intersections. Okay, and if I break the U1 winding symmetries by having dynamical Axion strings, then I again get the upper bound for the mass of the Z6 charged particle is upper bounded by the Axion string. So this is if there's a higher group symmetry. So I think that's pretty much everything I need to say about the symmetry structures. Just summarize that related to symmetry structure is that the Z6 symmetries will be broken to some invariable subgroup depending on whether K1 is divisible by 6 or not. And the things that we thought are broken actually becomes non-invariable. Okay, and then the things that are unbroken will actually form a higher group with the winding symmetries. So now using the symmetry structures, that we see that, for example, some symmetries, like for example the non-invariable symmetries, or the Z6 one from symmetries are actually subordinary compared to, for example, the magnetic symmetry and wine symmetries. So in particular, that means that if some of the symmetries that are more superior are broken, then the subordinary symmetries has to be broken. So from that, we can derive some inequalities. So that relate Z6 mass, so the mass of the Z6 particles, and then the magnetic monopoles and Axion strings. Okay, so I think that's pretty much everything I want to say.
Maybe a very naive question. You said in the beginning you standard gap models. How the models were quotient out by the Z6, right? So this magnetic monopole scale for the mass of the magnetic monopoles, this would in this case not come from the gap models, because the gap models would even have the Z6 symmetry from the beginning.
That's right. That's right. Yeah, that's right. Yeah. So this is some other completion.
No, but if you go below the scale of the monopoles, then it emerges, right? So it still gives you a non-trivial inequality.
So I think he was asking that if the UV completion is Axion guts. Sorry, the UV completion is Axion guts. Then
So that there's no Z6 to begin.
there's no even Z6 to begin. Don't get any. But of course, these inequalities are not super amazing. It's just we kind of expect monopole to be very, very heavy. But there's something that we can say based on the symmetries. Yeah. And it doesn't depend on UV completion.
Let's take that again.